go.
Today's topic is electric potential. The electrostatic force is a conservative force, and therefore we can describe electrostatic phenomena in terms of electrical potential energy. And from this we can derive a quantity called electric potential. It will not seem obvious at this level, but when you take the upper level electromagnetic theory class, electric potential is essentially the hardest part of solving an electrostatics problem. You might want to think of it in terms of this. Suppose I were interested in the force on a charge due to a group of charges or a blob of charge. What I would have to do then is to find the electric field due to the blob of charges and just multiply by that point charge of interest, and that would give me the force. It's not so easy to find the electric field, however. On the other hand, as you'll see in this series of lectures, if we can find an electric potential, we can simply take a gradient operation, you do the gradient operator on the electric potential, and then calculate the electric field, and then very simply come up with the electric force. So essentially, if you can find the potential due to a group of charges or a continuous charge distribution, you can almost immediately determine the electric field and then, of course, the force on some charge away from the distribution. That won't be obvious at this level because we're going to use electric potential as its own entity. One of the issues that we have, so learning electric potential is completely advantageous at the upper level. At this level, there are some pitfalls. And the one I want to point out immediately before we even start is the vocabulary that we use in physics, and it's kind of an unfortunate one. I'm going to write three terms on the board: electric potential, electric potential energy, and potential difference. To the novice student, these three terms sound almost interchangeable, and that's a huge problem. Electric potential energy is an energy, somewhat like gravitational potential energy. Electric potential is something that we can derive from potential energy in certain circumstances. Potential difference is a difference in electrical potential or electric potential between 2 points. That's important because when we talk about physical or lab situations, an electric potential difference is what you measure with a voltmeter. Potential difference and electric potential are measured in volts, and of course electrostatic potential energy, like all other energy that we use, is measured in joules or sometimes electron volts. So we want to try to keep these terms straight, and we'll do the best we can to make sure that you can differentiate between these three terms. The nice thing about electric potential that you will see at this level is it's a scalar function. Electric fields and electric forces are vector functions, and so solving problems involves getting components. Electric potential doesn't have that issue, and so solving many problems with electric potential are much more simple. So let's talk about potential difference and electric potential first. Suppose I place a test charge, call it Q0, in an electric field. The force on that test charge would just be Q0 times whatever the electric field is. And of course, they're vectors, and they would point in the same direction. If the charge is positive, they'd point in opposite directions if the charge was negative. The force is a vector sum of all the individual forces that are exerted on Q naught by whatever forces comprise E, whatever charges comprise E. F is conservative because any force governed by Coulomb's law is by definition conservative. Let's say that the charge moves some displacement, call it ds. We can say that the work required to move that charge some displacement ds is F dot ds, as we did in mechanics. This will cause a decrease in the potential energy of the electric field. We'll call it du, potential energy, as minus Q naught times E dot ds. So if the test charge moves from, let's say, point A to point B, the change in potential energy of the electric field, du, would be the difference between the potential energy at point B minus the potential energy at point A, which I could write as Q naught times the integral from A to B of E dot ds. This is what we call a path integral or a line integral. We're not going to be doing those in this class. We save those for the upper level class in electromagnetic theory. But happily for us, it's a conservative force, so the line integral is independent of path. It doesn't matter how you get from A to B, you're always going to get the same answer. So we define the electric potential, V, as the work or potential energy divided by the test charge. It's independent of the value of the test charge and has a unique value at any point in an electric field. Best off, it's a scalar quantity. And it has units of volts. So a volt then could be interpreted as a joule per coulomb. The potential energy is going to reside in the field itself, no matter how you put charges in the field. We can talk about a potential difference as the work it takes to move this charge from point A to point B. And in fact, only differences in potential are what we worry about. Generally, we measure a potential relative to ground, where we define the potential as 0. So one way to think about it is to say the potential, electric potential at a point can be written as the integral from, the negative integral from infinity to point P of E dot ds. This is the work required to bring a charge in from infinity and place it at point P. Also, we use as a unit of energy units called electron volts. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. It's the energy that it takes, or that a proton gains or loses, by moving through a potential of 1 volt. Let's look at potential differences in uniform electric fields. Let's consider a static uniform electric field, call it E. Let's say it's directed along the negative y-axis. Okay, here's the y-axis. We're going to have field directed along the negative y-axis. And suppose A and B are separated by some distance d. So here's point A, here's point B. We'll separate them by some distance, D. The potential difference between those points, between VB and VA, can be written as delta V, or the integral from A to B, negative integral, E dot ds, which I can write as minus integral from A to B, E times the cosine of 0 degrees ds, or integral of E ds from A to B, which will just be E times D. D is the distance between those points. And of course I carry through the negative sign. So very simply, by the way, the negative sign indicates that B is at a lower potential than A. In fact, electric field lines always point in the direction of increasing electric potential. So if a test charge moves from A to B, its change in potential energy will be delta U is the size of the charge, Q naught, times delta V, which is equal to minus Q naught E times D. So if Q naught is positive, delta U is negative. An electric field does work on a positive charge when the positive charge moves in the direction of the field. On the other hand, if Q is negative, in that case, delta U is positive. So the negative charge gains potential energy when it moves in the direction of the electric field. Let's look at electric potential and potential energy due to point charges. In the case of point charges, I can write my electric field as Q over 4 pi epsilon naught r squared. So BB minus BA can be written as 1 over 4 pi epsilon naught times Q integral of dr over r squared from A to B. And that's going to give me, it's going to give me minus 1 over r, so it will be Q over 4 pi epsilon naught r. Put in my limits from A to B. And I'll get Q over 4 pi epsilon naught B minus Q over 4 pi epsilon naught A. Now, I can say at this point, suppose we let A go to infinity. So if A goes to infinity, this term becomes 0. So the potential due to any point charge could be written as Q over 4 pi epsilon naught times R. And this is a valid expression for a point charge. If I have more than one point charge, all I have to do is the algebraic sum. It's the superposition of all of those charges at some point. So suppose I have a point P over here, and suppose I have, well, let's do something like this. Suppose I have a square, and I have 3 charges, Q3, Q2, Q1, and they're all, suppose they're all some distance r. the electric potential due to those points would be the sum of Qi over 4 pi epsilon naught r sub I. No vectors, no components, no nothing. So in this case, it would just be, for potential, it would be at point P, it would be Q1 over 4 pi epsilon naught R plus Q3 divided by 4 pi epsilon naught R plus Q2 divided by 4 pi epsilon naught square root of 2 times R. And that would be the total potential for that point charge. If I were to say, what would be the work I would have to do to bring another charge from infinity and put it at that corner? Then the work I would have to do, very simply, suppose I have some, we'll call it Q test. It would be just that value times the potential of that charge distribution, or the electrostatic work required, I should say, would be equal to Qt times the potential. On the other hand, we could also say that if I were to talk about how much work it would take to assemble 4 charges in a square, all I would have to do is calculate the potential energy between each of those charges. That is to say, I could write it as 1 over 4 pi epsilon naught Q1, Q2 over R plus 1 over 4 pi epsilon naught, in this case, Q2, Q3 over R plus 1 over 4 pi epsilon naught Q3, Q4 over R, plus then we have the two diagonals, 1 over 4 pi epsilon naught square root of 2R, and that would be Q1, Q3 plus Q2, Q4 over 4 pi epsilon naught square root of 2 times R. So all of that together would be the potential energy of this configuration. It would also be equivalently the amount of work I would have to do to bring 4 of these charges from infinity and put them in this configuration. Remember, just like in the mechanics class, the potential energy is an energy of configuration. It's how much work do I have to do to put a mass system or charge system in a particular configuration. What I'd like to do is pick up with this next time and talk about how we can get electric fields from electric potentials.